11, but a bit earlier than 11 today. So I can't keep on going on and on forever. And okay, let me do one more thing. Let's start. So what I will do is I will quickly give you an indication of the way in which the Frobenius method unfolds. I will not do the full calculation today because some of the details you will have to fill up yourself. And then start talking about continuous groups. Because we don't have much time, so I've got to sort of speed that up a bit. Okay. So basically what we were saying is something like this. We had this formula which told us if you have a group G with classes the C1, C2 and so on, each, and you have a subgroup of H, a subgroup H of G, then each class in C1, well, there could be elements in a class which are not in H at all. Some classes would be completely disjoint from H. Some classes would have some elements of H, but other elements will not. Some elements in H, other elements would not be in H. But the elements of the classes Ci which are in H, they break up into the complete classes of H. And similarly, K2 breaks up into K21, K22, and so on. And there would be situations where there are some classes for which there are no elements in common at all. And the point which the method that we talked about essentially was this, that if you know the characters of the irreducible representations for H, that is, you know the character values for each of these classes, K11, K12, and so on, and you know how the classes of G breaks up into H. That part, of course, has nothing to do with characters. That's simply standard group theory. Or the structure of the group G and its relationship with the subgroup H, you would be able to figure out a bunch of complex compound characters for capital G. And then using the irreducibility criterion and using the standard results that we have found out already of reducing representations, we should be able to use them to find out simple characters. And we already use this for S1, S2, S3, and so on. Not for S1, S2 so much, but for S3 and S4. And in principle, we can keep on continuing this till any Sn, but that would be way too cumbersome. And moreover, if you were to do it that way, to find out, say, the representations for S22, you would have to actually first find out S21, before that S20, before that S19, and so on. You have to do it all one after the other. However, there is another way in which you can do this, which is simply look at this way. We are looking for representations of Sn in particular, and if you have partition lambda of n, okay, this symbol essentially says lambda is a partition of n. That means is lambda is a bunch of a tuple of numbers, lambda 1, lambda 2, and so on. Okay, some people insist on this tuple being finite, in particular an n tuple. Some people insist on this being an infinite tuple with bunch of zeros at the end. That depends on which book you're reading. But the basic criterion is all these lambdas have to add up to n, and all the lambdas have this property. So all of them are non-negative and lambda 1, and they're ordered in a particular way. Now, of course, this ordering is simply to ensure that you don't overcount. You don't count 4 plus 1 and 1 plus 4 both as partitions. You just count one of them. Okay. Now, if you have such a partitioning, we have already seen the connection with partitions and the irreps of Sn in a sense, because there's a one-to-one correspondence between the partitions of n and the cycle structures which n can have, right? And the moment you have such a partitioning, such a connection, uh, remember the cycle structures of n determine the classes of n, and the classes of n immediately corresponds to the irreducible representations of the group Sn. Okay, so the moment you have so in general, by the way, this is a statement which is true in general, as you all know, that the number of irreps of a group is equal to the number of its classes. So there is a one-to-one correspondence between classes and irreps. Okay. That's well. That's all that is saying is that there are equal in number. Remember in standard, well, set theory or elementary mathematics, if you have two sets with the same number of elements, there's always a one-to-one correspondence between them. Okay, those two sets could be, say, a set of 10 apples and 10 marbles and whatever. But this one-to-one correspondence in general is not canonical. There's nothing special about that correspondence. There's nothing, no physical significance or mathematical significance to the particular correspondence you're looking at. That is the case also in group theory. It so happens that the number of classes equals the number of adepts. But and so in some sense there has to be a one-to-one correspondence between the classes and the adepts. But there is no canonical way in which you can say, okay, this class corresponds to this adept or vice versa. That kind of connection is not there in general group theory. It so happens that for the permutation group or the symmetric group, Sn, such a correspondence really exists. Each partition corresponds to a particular class, and as you will see, each partition also corresponds to a particular irreducible representation. Okay, so I will just quickly indicate one way in which that exploitation, that thing can be exploited, but I'm not going to do the full thing today. I'm just going to give you some hints of how this goes. Basically, what you do is given such a connection, such a partition. Of course, there are multiple partitions in the group Sn, but given any particular partition, what you can do is form this group.
Has Sir lost connection?
Yeah, looks like it.
Oh, okay. Hmm. sent him a text on Messenger, but he hasn't seen it yet. Can someone else also
E-
send him a text?
Even I sent him a text. He hasn't seen that either. He's probably continuing the class with walls.
Yeah.
Hey, can anybody tell me how long have been missing?
2 minutes, 2.5
2 minutes.
minutes.
Okay. Okay. I have to keep my phone. My phone is somewhere here. Yeah. Okay, Monica, you can stop calling me.
Sorry, sir.
I hope she. Yeah. Thanks for the call. Actually, somehow my phone is not even on silent, so I don't know why I can't see your. I didn't see any of your messages, and kept on going. Okay. So let's start the presentation again. So, anybody, please tell me what I was talking about just before we lost connection.
S lambda 1 cross S lambda 2.
Yeah, we were talking about the direct products. Okay, so we didn't miss much. So this was what we were talking about. So as I was saying that this is a subgroup, so it's a smaller, typically a smaller subgroup than Sn. Okay, the number of elements would of course be, number of elements here would be lambda 1 factorial times lambda 2 factorial times lambda n factorial. This of course has n factorial elements, so that may very well be quite, this might not be much larger than this product. So, so of course we are dealing with smaller subgroups, so that in itself is an advantage. But we actually, the Frobenius method actually hinges on the fact that Frobenius gave us this one formula which we already have studied before, that there's one particular compound character that you can always form, which is by exploiting the fact that the subgroup H, in this case the direct product here, has the identity representation as one of its irreps. Right? Because I hope all of you remember this, that basically the formula that came out was something like this. You would have to take the number of elements of G, divide by the number of elements of H, then you have to sum up over all the phi's. I have forgotten what notation I was using, where the sum is over all the k's which actually belong to C. Okay, I'm just sort of abbreviating the notation a bit. When I say K belongs to C, I mean subclasses of H which were completely contained into the class C, and you had this kind of a formula. Okay, you remember this? That was what we did the last day. But we also said that we can always take the identity representation in which phi k is just 1, and then when you sum up over all k belonging to C, all you really get is how many elements of C are there in H, right? Because every element of C which belongs to H belongs to some class of H or the other, and when you add them all together, you just get the number. So this is basically the formula we have. I hope this is clear to everybody. Is there any confusion about this one?
No, sir.
Okay. So this is a simpler version of the general formula that we had. The general formula talked about any character or any representation on any irrep of H. This is the simpler version we get just by exploiting the identity representation of H. Now, when we say in the previous example that we talked about, when we were trying to say figure out S4 from S3, what we saw was that the identity representation gave us one compound character. Then, of course, that's only one compound character. We would want more, right? Because the number of classes of S4, of course, exceeds just the identity representation and the alternative representation by more than one. So there's more than one compound character to be found out. And so we had to exploit other representations of S3 as well to go to to find S4's character table. Now, for this particular case, what happens is, well, just take a look at the numbers. How many classes does Sn have? Yes? How many conjugacy classes? I'm not asking for a closed formula. I'm just asking what is it equal to, the number of classes of Sn.
Number of ways n can be partitioned.
Yeah, number of partitions of n. And each partition of n corresponds to one such subgroup, right? So what we have here is one of these special subgroups. You have exactly as many of them as you have irreps of Sn, right? Because as you have classes of Sn, that means you have irreps of Sn. This connection between partitions and classes and irreps, that becomes very handy here. So every time you break up n into a partition, that gives rise to one compound character. And so you have as many compound characters as irreps. Now, of course, that doesn't end, that doesn't prove that that's all you ever need, for the simple reason that it's very possible that some of the irreps could be what? Could be simply repeated. Right? Some of the compound characters could be just dependent on each other. Remember, if you have n compound characters and you want to find, not n, okay, let's not call that n, let's call that phi n, number of partitions of n. So you have phi n compound characters and phi n characters to find from there, simple characters to find from there. If these compound characters are all independent, you should be able to work your way through to that. However, what if it's dependent? So what Frobenius actually went on to prove is that these compound characters are all independent. So if you find out all the compound characters using these partitions, you are actually through. You actually have enough number of compound characters to build up the entire character table. Okay. Of course, you only get compound characters this way, not simple characters. So you still have the task of converting those compound characters to simple characters, but you have enough information by just following this procedure and just using the identity representation for each one of the subgroups. But what is really important is actually using this formula becomes rather simple for Sn. And why is that? Basically, the reason is that the number of elements in a class, that's actually quite easy to figure out. There's a nice, simple formula for that. Well, not necessarily very simple, but not too complicated either. So as we said, a class, say, how would you characterize the class C of Sn? You would characterize it by saying the alpha 1 cycles, beta 2 cycles, gamma 3 cycles, and so on. So what are the conditions that you have on these numbers? One of the conditions, of course, is alpha plus 2 beta plus 3 gamma plus, well, all of these numbers added together must be n, right? Because that's just how many elements you have that are being permuted. And the number of elements in a class, so basically what we have been calling NC. So if a class is given by number of these cycles, alpha 1 cycles, beta 2 cycles, and so on, we know what the number is. It's just simply n factorial divided by 1 to the alpha, alpha factorial, 2 to the beta, beta factorial, right? Is that okay? These numbers are simply how many distinct permutations you have with the same cycle structure. And remember, we had already figured out that in Sn, what happens is every element with the same cycle structure is in the same class. Is that okay? I hope everybody remembers that.
Yes, sir.
Okay, now the important thing is to figure out what this number of elements in C intersection H is going to be, right? So how do you go about doing that? Let's focus on how would a element of this kind, okay, be a member of this. So this, we are talking about permutation of n objects with alpha 1 cycles, beta 2 cycles, gamma 3 cycles, and so on. So, and you are claiming that that element is a member of this direct product group. How can that happen? That is, what possible structure would you want from the subgroups here? Suppose, let's just say, suppose the class you're looking at has 5 2 cycles. Okay, where can the 5 2 cycles come from in this direct product? Of course, because we are only focusing on those elements here which are also here, we have to now find out how we can have 5 2 cycles from an element here. How can I have 5 2 cycles in an element here? Yes? Any ideas? How can you have 5 2 cycles in an element from this?
One of the lambda 2 should be 2. No, lambda 2 and lambda 3 should differ by 5.
Sorry, your lambda 2 and lambda 3 should differ by 5. That's what you're saying.
Yes, sir.
Lambda 1, okay, let me just remind you, lambda 1 is a permutation of the first lambda 1 objects. S lambda 2 is a permutation of the next lambda 2 objects.
Then we should have 5.
And these permutations, of course, will have cycles of their own, right?
Then we should have 5 lambdas.
So, 5 lambdas. I don't really get you. I'm not sure whether. Okay, am I being able to get the question across? Suppose I'm looking at a particular class of Sn, which has a different cycle structure. I'm just saying, let's say for the timing, beta is 5. That is, number of 2 cycles in the class I'm looking at. That happens to be 5. So how can such an element be a member of this direct product set? First of all, let me just make this very clear, although I think it's pretty clear to all of you, that not all elements of Sn will be members here, right? For example, something which permutes an object here to an object with an object here. That will not, even a 2 cycle, let's say one element here switches with one element here, switches place. That's a 2 cycle. But such an element will, of course, not be in the direct product state. The direct product only involves first lambda 1 is permuted, next lambda 2, next lambda 3, and so on.
So 5 lambda I should have the value 2. And then we will have the S2 cross S2 structure, which essentially means there are 5 2 cycles.
So where should the 5 2 cycles be? In lambda 1 or lambda 2 or lambda 3 or which ones? First of all, in order that an element Sn be at all an element here, means that whatever cycles you have that have to essentially fit inside these. It can't be, as I said, you can't have a 2 cycle which swaps an element here with an element here. That's not allowed. That's, of course, an element in that class, but that's not an element in the intersection of C with H. So you need 5 2 cycles. But where will the two cycles come from? Will they come from lambda 1 or lambda 2 or lambda 3 or what?
Sir, I
Okay,
couldn't
this is an
understand
example.
your.
Okay, let me just maybe I will make it more specific by looking at a particular example. Let's say we are looking at S10, and 10 has several partitions, but this is one of them, 5 plus 3 plus 2, right? So you have 5 objects, 3 objects, and 2 objects. Let me, okay, in this case, that's a bit too, okay, 5 objects, 3 objects, and 2 objects. Okay. Of course, all the objects can be permuted in S10, but right now we are looking at this particular permutation. So we are looking at S10, a subgroup of S10, which is S5, direct product S3, direct product S2. Right? S10 contains this as a subgroup. And let's say, instead of looking at, say, beta is 3 now, because we have only 10 elements, taking 5 2 cycles, maybe just pushing it too much. Let's say you need 3 2 cycles. Okay. Now the 3 2 cycles could 2 cycles means 2 elements are being switched. But where would the 3 2 cycles come from? In this one. In this.
Either S5 or S3. So S5 two cycles and S3 can have one 2 cycle. S2 one. Yeah, even have 2 cycles. Yes.
The point is simple. Okay, I was asking a very, very simple question. All I was saying is you could have beta 1 2 cycles here, beta 2 2 cycles here, beta 3 2 cycles here. Right? Of course, beta 3 could be either 0 or 1. There's no other possibility. Same for beta 2, by the way. For beta 1, the possibility is 0, 1, and 2. Right? You just look at how many 2 cycles are at all possible. You can't have 3 2 cycles in S5, right? S5 doesn't have enough elements to support 3 2 cycles. But you can have 0, 1, or 2 cycles here. You can have 0 or 1 2 cycles here, 0 or 1 2 cycles here. Right? Is it okay?
Sir, 3 cycles splits
Well, you
into
could
2 cycles, right?
Is this hello?
A 3 cycle.
Monica, you were saying
3
something.
cycles splits into 2 cycles, right?
No, I am not saying 3 cycles. Beta is the number of 2 cycles. There are 3 2 cycles in the particular class of S10 I'm looking at. 2 cycles, not 3 cycles. The 3 here is just the number of 2
beta
cycles.
2 can either be 0 or 1, but a 3 cycle can split into 2 cycles.
No, beta 2 is the number of 2 cycles
yes,
in this.
So a 3 cycle.
How many 2 cycles can
Can't
you
you
have?
split a 3 cycle into 2 cycles?
Take any permutation of 3 objects. Okay, if you have a permutation of 3 objects, how many 2 cycles can you have then?
Oh, okay. Yeah.
Remember, cycle structure means, okay, this would be one thing which has a single 2 cycle, right? That's not the only one. There are many other possibilities, right? You could also have this, which have no 2 cycles at all.
Oh,
right?
okay.
2 cycles don't mean transposition. 2 cycles mean 2 cycles, just 2 elements being cycled among each other. This has no 2 cycles, right? This is number of 2 cycles here is 0. Number of 2 cycles here is 1. But you cannot have more than 1 2 cycle here simply because you don't have enough elements, right?
Got it, sir. Sorry.
Is it okay?
Yes, sir.
Hello?
I was thinking S3 in terms of just 3 cycles, like not as S3 as a subgroup of 3 permutation 3.
No, S3 is S3, symmetric group of 3 elements.
Yeah, I got confused there.
5 is a 5, symmetric group of 5 elements. Okay. Right? Is it clear now?
Yes.
S10 is a set of all permutations 10 objects. What you are saying is let's permute the first 5 of the 10 objects, the next 3 among themselves, next 2 among themselves. Any permutations, not just cycles. Okay, not just cycles of all the objects. So here it's possible to have two cycles at most. You can't have more than two cycles, but you can have up to two. Okay, right? Is that clear now?
Yes, sir.
You may, of course, have this cycle 1, 2, 3, 4, 5, which has no two cycles at all. You could also, of course, have 1, 2, 3, 4, 1, 3, 4, 2, say 5. That also has no two cycles. Okay?
Yes,
Yeah?
sir. Got it.
Or 1, 2, 3, 4, 5. Again, no two cycles. But you would also have elements like 1, 2, 3, 4, and 5, which have two cycles. All I'm saying, I'm talking about the first S5 here. Is it okay with everybody? So the point I'm trying to make is, if your final, if a class that you're looking at for S10 has 3 two cycles, and if the element corresponding to that class also belongs to H, then the 3 two cycles have to come from somewhere. Where will they come from? They can in fact come from any one of these subgroups, S5, S3, or S2. But the important restriction is, whatever beta you have, that must be equal to beta 1 plus beta 2 plus beta 3 plus so on. Is it okay? That's sort of trivial, right? Is this okay with everybody?
Yes, sir.
All you really need is, remember our class in Sn is characterized by alpha 1 cycles, beta 2 cycles, and so on. Then we will say, okay, fine, the alpha 1 cycles must come from somewhere. So there will be alpha 1 cycles in the first, in lambda 1, in S lambda 1, alpha 2, in S lambda 2, alpha 3, in S lambda 3, and so on. So remember, this is what we are looking at. Sn contains this. You must have this. Beta also must have this. The reason why I'm
Sir,
ending all these at n, yeah,
sir, could I just suggest something? You in the
yeah,
previous
go
few
ahead.
lectures you used KIs instead of alphas and betas. That so like
No, I did not use KIs instead of alphas and betas. I think you are mixing up. The case where the classes, okay, C's were
I
the classes of G, K's were the classes of H. The alphas and
yes
betas are not the classes. Alphas and betas are the number of cycles in each class. They characterize the classes. So a given class in C, in even a given class C of G, is not characterized by a single number alpha or beta. It's actually alpha, beta, gamma, the entire set. That is, how many 1 cycles, how many 2 cycles, how many 3 cycles, how many 4 cycles, etc. that particular class has.
hmm.
Let me remind you once again, Sn is the cycle
Okay.
structure which determines the class. So alpha, beta, gamma are just numbers. They're just integers. They're non-negative integers. They're just the number of 1 cycles, 2 cycles, 3 cycles, 4 cycles, etc. corresponding to a particular class. Okay? Alpha 1,
But you
alpha 2,
used
alpha 3 means that. Hmm?
yes, but
Yeah.
you used KI cycles while uh, showing that formula in factorial by I to the power KI into KI factorial multiplication over I.
Oh, I did that, right?
Yes,
That
so
may be a bit
isn't
of a,
that
that would be a bit more confusing, because unfortunately I did that, but that would be a bit confusing for the simple reason that I'm using, in the last lecture I used K's and C's in an entirely different manner.
yes, yes, yes.
C's were
Okay, okay.
classes of G and K's were classes of
Classes in
H.
H.
And
Yes.
alpha betas are standard notation, so let's stick to this.
Okay, sir. Okay, sir.
I may have messed up my notation by making it up as I go along, so that's possible. But I think this is pretty standard, so, and so on. The question that I have for you is, how many elements of a particular class characterized by alpha, beta, gamma, and so on belongs to H. So how would you find that out? Well, remember, all you are saying is alpha, beta, gamma essentially breaks up into alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2, and so on. So if you focus on, say, a particular subgroup, say lambda S lambda I, the number of elements with alpha I, beta I, gamma I there is simply going to be lambda I factorial by 1 to the alpha I. Right? These are the number of elements in this particular class in S lambda I. Is it okay? Okay, let me just give you this specific example once again. Let's say I'm looking at a particular class of S10 where cycle structures is, let's say, 4 1 cycles. Okay, and that leaves us 6 elements. So alpha is equal to 4. Let's say beta equals 0 and gamma equals 2. Let's check whether that makes up 10 elements. Does it? It does, right?
Yes, sir.
Alpha equals 4 is 4 1 4 elements. This is 0, of course. This is 2 times 3, that's 6 elements. So this is a possible cycle structure representing a particular class in S10. Now, this would correspond to several alpha, beta, gamma scenarios. Let's say one possible scenario is this. 3 1 cycles from here. Okay. Of course, there are no 2 cycles. And once 3 1 cycles are gone, you can't have any 3 cycles anyway from here. Okay, that's of course impossible, by the way. Can you see why that's impossible? You can't have 3 1 cycles all from here. Can you see why?
Because we need a 3 cycle, or 2 3 cycles.
We need 2 3 cycles, and 1 3 cycle, of course, can come from here. In fact, in this case, I have actually taken a very constrained situation because in the example I have taken, this has to have a 3 cycle. In fact, the 3 cycles have to come from here and here. Right? There's no other possibility. That means to get alpha equal to 4, the only way that's possible is alpha 1 has to be 2, right? Because once gamma 1 is 1, that only leaves 2 more elements. So you can have it here, and no elements are left here. And alpha 2 is 2. Is that okay? That's the only way this can split up. Of course, beta 1 has to be 0 throughout. Beta 1, beta 2. So alpha 2 is 0, beta 2 is 0. And here. So that actually is the only way the 4, 0, 2 can split up. There's only one possible combination of alpha 1, beta 1, gamma 1, alpha 2, beta 2, gamma 2, and alpha 3, beta 3, gamma 3. Is this clear to everybody? That's because we want to keep the total numbers correct. Sometimes, in fact, more often than not, there will be multiple ways of distributing alpha I, beta I, gamma I, not so constrained as in this case. Is this clear to everybody?
Yes, sir.
So what we said was 4, beta equals 0, gamma equals 2. That's one possible class from S10. And the only way that can work out in our 532 scenario, of course, that's not the only partition, but that's the partition we are looking at right now, is that alpha 1, beta 1, gamma 1 would have very specific values. In fact, what you can have only is 201, 001, and 200. all the alphas add up to alpha 1s, alpha i's add up to 4, beta i's of course add up to 0, and gamma i's add up to 2. And this is the only way you can achieve this given this particular scenario, right? Is that okay? And just to give you another example, maybe 3, with the 3 gone, beta equals 2 and gamma equals 1. Now you have several choices, right? Because gamma equals 1 immediately tells you that that either the 3 cycle could come from here. So one possibility will be 0, 0, 1, the 3 cycle comes from here, right? Of course, if the 3 cycle comes from here, you know that there are no 3 cycles here because the only 3 cycle is gone. But now you have 2 cycles to play with. So where would you put the 2 cycles? You can put both of them here, none here, right? Of course, that means this is one possibility. But this is not the only way of distributing alpha I, beta I, gamma I in this case. As you can see, you can also put a 3 cycle instead of here, you can put it in the first block and so on. There are several possibilities in this case. In most situations, you will have multiple ways of distributing alpha I, beta I, gamma I so that this will work. This is okay. Unfortunately, I took a very specific example to begin with, that of 402, which had only one possible distribution of alpha I, beta I, gamma I. I don't want you to go away with the idea that that's going to happen all the time. That's not going to happen most of the time. Okay? So basically what you have this relationship that alpha has to be sum of alpha i's, beta has to be sum of beta i's, and so on. And the number of, okay, now let's focus on number of elements in this class. 201. How do you get the number of elements there? That's simply 5 factorial by 1 to the 2, 2 factorial, and nothing coming from the 0. But anyway, let's write that down anyway. 2 to the 0, 0 factorial, and 3 to the power 1, 1 factorial. Right? So that's the number of elements in this particular class of S5. Then you can find out the number of elements in the particular class in S3 and the number of elements in S2. And if you multiply them all together, what you get is the number of elements in C intersection H corresponding to this particular split of alpha I, beta I, gamma I. Am I making this clear? In other words, if you look at lambda I, S lambda I, the number of elements in the corresponding class there and you have to multiply over all the permutations, all the partitions. But that's not all. That's just one way of distributing alpha, beta, gammas among them. So you have to sum up over all possible ways.
So shouldn't
But the
we,
all possible ways, yeah.
shouldn't we multiply
Hello?
over all i's?
Yeah, all i's actually. So all partitions essentially means all i's. Yeah, right. So maybe if I'm already using i's, I can just say all i's. Right. And then what you do is, okay, so sorry, you were right, not over all partitions, for a specific partition. So this should be all over all i's from 1 to n. And then you have to sum over all the possible ways in which the alpha i's could be distributed. So this is sum over all alpha beta gamma distributions possible, with this constraint being added, and so on. And not only this, you also have to have this alpha I plus 2 beta I plus 3 gamma I, all these constraints is equal to lambda I, right? And that has to work for all the i's. So subject to all these constraints, how many ways can you distribute them? Okay. Seems the real problem here is getting all these constraints in place. But once you have this, it's really rather easy to figure out the ratio. This ratio, the compound character that we have, if you look at that, the formula was mod G by mod H n C intersection H by NC. Okay. Now, notice that when you divide mod G by NC, mod G had, how much was mod G? Mod G was simply n factorial. What was NC? This is mod G. NC, of course, was nothing but n factorial divided by 1 to the alpha, alpha factorial, 2 to the beta, beta factorial, and so on. So when you divide these, the n factorial cancels out, right? You just have 1 to the alpha, alpha factorial, 2 to the beta, beta factorial, and so on. That's mod G by NC. What do you get when you divide this? Remember, this is basically what NC intersection H has, right? But you're going to divide it by mod H. What will happen? Well, what is mod H, by the way?
Lambda I factorial, lambda 1 factorial.
Lambda 1 factorial times lambda 2 factorial up to lambda n factorial, right? So you divide that, all the lambda factorials go away. Okay? Right? Remember, this is in the numerator here. You're going to divide this by the product of all the lambda factorials, that this just goes away. You are left with this. And, of course, the sum. Sum over all possible ways of partitioning the alpha i's. Alphas into alpha i's, beta i's, and so on. But if you do that, you should realize one thing also happens. The 1 to the alpha I. Okay? When you multiply this over all i's, what do you get? You get 1 to the alpha. Okay, 1 to the alpha is another trivial because that's always 1. But let's focus on the 2 to the beta I. So get 2 to the beta 1, 2 to the beta 2, 2 to the beta 3, 2 to the beta n. Right? How much is that?
2 power beta.
So the 2 power beta also cancels. 3 power gamma cancels. This in the numerator, these terms will just cancel out. Okay? You will be left with alpha 1 factorial, alpha 2 factorial, alpha n factorial, beta 1 factorial. So ultimately, the formula simply becomes alpha factorial divided by alpha 1 factorial, alpha 2 factorial, alpha n factorial, beta factorial divided by beta 1 factorial, and so on. Of course, the sum is still there, but the only thing that you remember in the sum is you have to have these conditions. Now, is this okay? Everything else cancels out. So all this lambda factorials, etc., drop out. The powers drop out. You're just left with these factors. But if you're left with these factors, this should immediately remind you of a kind of problem you used to do when you were in class 12. What are these coefficients?
Permutations.
Yeah, but where else can you find such things?
These are the coefficients in a multinomial expansion.
These are coefficients in a multinomial expansion. Exactly. But it's a constrained kind of multinomial expansion where these conditions have to be held. Okay. So the next step in the Frobenius method is very simple. It's just an attempt to figure out a multinomial in which you will get these as coefficients with these things here obeyed. Now, this is something which I'm pretty sure most of you have done at least once in your life in class 12 or later at least with 2 variables, if not more. So I will leave this as a hint. Think about this. Try to figure out how to express this coefficient, this quantity, this number, as the coefficients of a polynomial or a multinomial. That's really more precise. What multinomial it is, such that you will have these quantities exactly as coefficients of a particular multinomial expansion in multiple variables. So basically, you want to look at some function of x1, x2, xn, which when you expand it out, the x1 to the lambda 1, x2 to the lambda 2, etc., we'll have a coefficient which is given by this. So this really is the crux of Frobenius's method, just looking for this particular multinomial properly. And once you have found out that, if you interpret that as a combinatorial problem, from there everything about these Young's tableaus, etc., fall. So that's what I was trying to drive at. So this is an exercise for you. This is something which you should be able to figure out on your own. Just think back at class 12. Okay. Say, just to give you a hint, suppose you had a problem like this. And then asked, what is the coefficient of x to the power, say, 11 y to the power 13 from here? Notice that this extra 11 can either come from here or from here. But if it came from here, say, it could come from alpha here, alpha 1 here, and alpha 2 here. But if it came from here, it would come with the 2 alpha 2 equals 11. So you will end up with alpha 1 excess here, alpha 2 excess from here, alpha 2 x squares from here. But that would immediately give you the alpha 1 plus 2 alpha 2 equals 11. Now you don't want that, but you do want alpha 1 plus 2 beta 1, etc. So basically you want alpha factors from here, beta factors from here, and so on. So just try to recast this demand that you have, that these must sum up to lambda i's, in the form of a polynomial expansion like this. I've written with only 2 variables, but you can write with more than 2 variables and get these constraints exactly in place. So work this out. We will take a break from this particular topic right now. We are going to come back to this later. So by the time, say, 3 or 4 classes are gone, I would expect all of you to work out this on your own. Once again, as I've said, this is really simple. This is ordinary perturbation theory. No, sorry, ordinary number theory. Not even number theory, ordinary algebra at class 12 level. Although at class 12, you did it with 2 variables at most. So is the question clear? Find out the multinomial whose coefficients will give you these quantities. Once you have found that out, the rest of the calculation becomes sort of routine. Am I still here, or?
No, sir, you're not.
Yes, sir, the question is
I am
clear.
here, but you people seem to be completely.
We got the question.
You got the question? Okay, good. Great. So now what we will do is we will take a break from SN and its representations. We will come back to this. Hopefully, by the time we end this course, we will have enough time to come back to how this translates to Young tableaus, especially more so because the representation theory for SU, the special unitary groups, can be done very nicely in terms of the Young tableaus. And for that, you have to, if you want to understand that, you have to go via this result. Okay. But before I go there, let me just quickly, did I tell you about the hook results? The hook formulae? You didn't, right?
Yes, sir.
Did I? Yes or no?
Yes, sir.
I talked about that, right?
N factorial by some, multiplication over k into the hooks.
Yeah. The hooks. Yeah, I did talk
That one,
about
right?
that. Okay, so fine. So that is the result that we
Yes.
will need. So even if we can't derive all the results in the way, that's one thing you will have to sort of mug up. At least it's a pretty easy formula to mug up. Not so easy to derive, as I said. Uh, I did give you a proof, right? Completely messed up wrong proof.
Yes.
Yeah, that's a wrong proof, but it gives you the right answer. So it's a pretty good way of remembering what the result is. Okay, but that result at least we will need because we will have to talk about irreps of SN. So even if we don't have enough time to go through the full theory, which at this pace it seems that I won't, or at this pace it might even take up the entire rest of the semester, which I don't really want to talk about spend here. So we will talk about continuous groups next. That one thing we'll keep in abeyance. Hopefully, we will come to the entire proof. Even if we don't come to the entire proof, that result will be very important for us. Okay, so but before I go into continuous groups, let me just ask you this: how much of continuous groups you already know? The Lie group Lie algebra connection, you already know that. Yes, no, maybe. Some of you definitely know about the Karta subalgebra and stuff like that, right? In Lie algebras.
Sir, I don't know about your algebraic topology course last semester, but apart from that, we weren't introduced to it exactly.
The algebraic topology course last semester was algebraic topology. That has nothing to do with
I mean,
Lie groups or Lie algebras.
I don't know if any hints were given in that course, but apart from that, we weren't introduced.
You were not introduced to Lie groups or Lie algebras at all.
Sir, I don't know anything.
Okay, so that sort of okay. That means that we will have to state a lot of results without any proof, okay? Because we'll have a lot of ground to cover. Okay, but before we go into that, let me just ask you one thing. You all know this SO3 SU2 correspondence. That much you do know, right? There's corresponding to every rotation. There's an SU2. There are actually two SU2 elements and so on. You know um, about the manifold structure of SO3 and SU2, why SO3 is doubly connected, SU2 is singly connected, and so on.
Oh God.
Yes, no. But say that quickly. I have very little time today, so because my wife who has to take a class here will kick me
Uh,
out
I
very
mean,
soon.
it feels
It
like we
it
have come across it at some point, but personally, I don't remember exactly.
it was
Okay,
just
fine.
stated.
So let me quickly just
It was just stated and
okay.
used.
So let me just quickly tell you about SO3 first. SO3 is of course the set of all 3 by 3 orthogonal matrices. And as you all know that SO3 has a one-to-one correspondence with a set of all rotations that you can carry out in physical space. Okay, by the way, when I say as you all know, you should immediately stop me if that's not the case. Okay. But anyway, every rotation corresponds to a 3 by 3 orthogonal matrix. This much we already know, and we have already derived why this rotation matrix has to be orthogonal and so on. And not only that, we have also talked about why it has to be determinant 1, right, rather than determinant minus 1. So SO3 is not only just 3 by 3 orthogonal matrices, these are 3 by 3 orthogonal unimodular matrices. Okay. So basically, this is a bunch of this is a continuous group. Why is that a continuous group? Because there's a parameter on which, or not one parameter, but a set of parameters on which the group elements continuously depend. Now, there's a much more rigorous way of stating this, but I'm just hoping to rely on your intuition at this stage because the rigorous statements would take way too long.
Sir, like
Yeah.
does it is it enough to prove a homomorphism between these two groups? Like I'm assuming both of them will have equal number of parameters. So if the group algebra holds true, is that enough to show the
Yeah.
equivalence?
Show the?
Equivalence between both the groups?
Not really. There's a more explicit version than that. But right now, we are not even going to talk about SU2 today. I don't have the time to cover SU2 today. We'll talk about that the next day. But let me just talk about the group manifold for SO3 and why that's a complicated thing. And then you will see why SU2 is simpler. So if you want to parameterize a rotation, what do you need to do? What's the easiest way of parameterizing a rotation? If you want to specify rotation, what would you actually specify? Tell me that. That's easy, right?
The angle.
The angle alone will not do, right? There is a rotation in three dimensions. The axis and the angle, right? You have to specify, let's say, a unit vector n hat along the axis and an angle theta for the rotation. That you have to specify. Is that okay? So you could say, give me all possible unit vectors in all possible directions and the angle theta of rotation. That gives me the group manifold. That is, corresponding to each n hat and theta, these are the parameters specifying the rotation. You have a rotation corresponding to n hat and theta. But there's a catch there. The catch is, how big can theta be? This angle of rotation? Can it be any value or is there a restriction? Remember, we want a one-to-one correspondence between my parameter space and the rotations. I don't want to have multiple rotations corresponding to the same parameter or vice versa. Multiple parameters corresponding to the same rotation. Then there should be an obvious restriction at least on theta. What should that restriction be?
2 pi.
0 to 2 pi.
Well, actually, not 0 to 2 pi.
0 to pi, and you will include only 0 or only pi.
Only?
And it will be a interval from 0 to pi, but will be closed from one end and open from another end.
That would be bad because that way you will lose one rotation completely. That it's not as simple as that. But your point is okay because in the sense that if this is an allowed vector, so is this, right? Minus n hat. And if you say, let's say you say 330-degree rotation about n hat, the same as 30-degree rotation about minus n hat. So if you allow 0 to 2 pi, the trouble is the same rotation will be counted twice. You don't want that. Once for 330-degree about this axis, once for 30-degree about this axis. Is this clear to everybody? You don't want overcounting. So when you say this is the group manifold, you mean that every point in the manifold pertains to one group element. And this connection has to be continuous and so on for a continuous group to be there. And smooth. And in some more senses to get a V group. But we are going to talk about that later. For the time being, let's focus on this particular group. So here, theta has to be actually between 0 to pi. What you said a while ago is it should be something like this. It should be either 0 or this. But neither of them work, by the way. If you take this one, then the identity rotation drops out of your parameter space. Right? If you don't allow 0, then there is no identity in your parameter space, so you don't even have a group. And you leave this out, then the 180-degree rotation, if you take this one, for example, that is you keep 0 but you leave pi out, then the 180-degree rotation will never figure in your group space. Okay, so it can't be one-sided. It has to be both-sided. But with a catch, of course. But one-sided one will not work. If you just took a one-sided interval with either 0 in and pi out or pi in and 0 out, you will be leaving out a bunch of elements. Okay? Yeah?
Sir, but if we take
is it okay with everybody?
Yeah, but if we take pi, then we have two rotations, right? Like pi with respect to n hat and pi
Yeah, so
with.
that's a problem. But I understand that that's a problem, but that is a problem we have to deal with. We simply can't leave out pi because then we will completely not have that rotation at all. I
Hmm.
agree that that's a problem. Keeping 0 pi, which is what I'm insisting, that doesn't solve the problem. But not keeping 0 or pi will simply not work because you're leaving out elements. Okay.
We could put the first interval for n hat and second interval for the minus n hat or something.
Well, yeah, in a way, but there's an easier way. That way where the two join together. Of course, you have to decide which one is n hat, which one is minus n hat, right? Because there's a unique way of having a positive vector. In 3D, there's no ordering. But you have to, if you artificially put in a way like that, then on the boundary where these two meet, you will just think about it, you will leave out some rotations.
Hmm. Yes. Yeah. Yeah.
It will work everywhere else, but on the boundary where these two regions meet, you will get into trouble.
Hmm. Hmm. Okay.
All these simple-minded ways actually have problems. But let me just quickly tell you what the parameter space is going to be like. Uh, well, instead of specifying the n hat and the angle theta, you can actually cheat a bit. You can just say, just take a vector theta, which is a vector whose magnitude is theta and length and direction is n hat. That way, both theta and n hat is encased in a single vector, right? So let's forget about this pi angle business for the time being. Let's just focus on getting the parameterization done as much as we can. Instead of specifying both n hat and theta as separate elements, what we can always do is take a vector theta n hat. Is that okay?
Yes, sir.
That will have the same information as the magnitude theta and the direction, right? Now, if you take, but of course, theta has this situation because we are keeping theta between this. This theta has to obey this. Of course, I've already written that. But that means we have vectors whose lengths are bounded by pi. All vectors whose length is bounded by pi. So what does it give you? All vectors whose length is bounded by pi. You take the bunch of all vectors, take them all together. What do you get?
A solid sphere of radius pi.
What? Huh?
Solid sphere
What of?
of.
I couldn't get that.
Huh, sir?
Well, a ball, a solid sphere is a sort of physicist terminology. What you really mean is a ball. That's the mathematician's way of talking about what a solid sphere is, not just the surface, but all of it, of radius pi. Okay, but now comes this catch. All this is fine, but there's a problem. The problem is, if you're right on the surface, then you have 2 points on the surface, 2 antipodal points, which actually talk about exactly the same rotation. Okay? Right? So what you end up with is that if you want one-to-one correspondence between the group manifold and SO3, the only way you can achieve that is by saying, okay, my group manifold is a solid ball of radius pi, but with antipodal points on the surface identified to each other. That means it's not just any ordinary sphere. It is a sphere where a point here and a point on the surface in the other side, they have to be treated as the same point. Is it okay? If you do that for all such points, all such pairs of points, then you get the group manifold of SO3. The group manifold of SO3 is a rather complicated object. It's not a very simple kind of set which you can easily visualize in 3 dimensions. Okay? Is that clear to everybody?
Yes, sir.
Okay, and this actually leads to one very important difference, which is, suppose you wait. So the each point in this space, of course, corresponds to a particular rotation. So if I have a loop in this space, what does it really mean? It means that you're starting from a given rotation. You're keeping on changing the rotation slightly as you move along the loop. When you come back, you are back to the same rotation. So you're completing a loop in SO3. Is it okay? That is, you start with a particular rotation, keep on changing the rotation slightly, and ultimately you're back to the same rotation. That's what a loop will give you. Okay? Right? Yes or
Yes,
no?
sir.
Yes, sir.
Then you can think of doing a slightly smaller, going to a slightly smaller loop, and a smaller loop, and a smaller loop until you shrink the loop down to a point. Which means you can condense any loop that you have in SO3 of this kind, where you're starting at a particular rotation, going around in and changing the rotation slightly until you come back to the original. You can keep on changing this particular loop continuously until you end up with a loop which is don't move from your rotation at all. You stay where you are. That is, it becomes a single point. A loop shrinks to a single point. Okay? Clear?
Yes, sir.
However, SO3 also has loops of this kind. This is a loop, by the way. This doesn't look like a loop, but it is. It starts at a given rotation, ends at exactly the same rotation. Is that okay? Because the two antibodal points, remember, refer to exactly the same rotation. They are 180 rotations about one axis and 180 rotation about the opposite axis, but they're exactly the same rotation, right?
Yes, sir.
Now, the problem is if you want to shrink this loop down to a point without breaking it, keeping it a loop, you simply can't, right? Why? Because suppose you want to, say, detach this point. You can't detach this point. The moment you detach this point, it's no longer a loop. If you move this point, but you want to keep it a loop, then this point will move to the corresponding antipodal point. So it will still stay a stretched thing between two sides. Okay? Yeah? So
Okay, sir.
SO3 is not simple or simply connected. In other words, that means there are loops in SO3 which cannot be shrunk to a point. Okay, in algebraic topology, we would say the fundamental group of SO3 is not trivial. But that's the important point is SO3 has loops which are not contractible to a point. But there's one more thing. Suppose you had a loop like this in SO3. Let me just erase a bit of. Okay, let's. Okay, so this is a loop that I've drawn. That, by the way, is going all the way around the parameter space. You're back to the original rotation. But now let's say you have another loop. That is, you do it twice. Two rotations are connected one after the other. But can you now see that you can shrink this while keeping it a loop to a point? Because now I can detach this point because it still stays a loop because you're back where you were. Can you see what I'm trying to say? This one is one full
Yes,
360
sir.
rotation, you're back to where you were. There's another one, two 360 rotations, one after the other, carried out is a 720 rotation. Classical physics, we say 360 means nothing. And 720 is simply two 360, so of course that's also nothing. But you should see that there's a big difference. 360 rotations are not contactable, so they can have physical effects. 720 rotations, on the other hand, can be smoothly deformed down to no rotation. That means 720 rotations may end up giving you no physical effect. In fact, will end up giving you no physical effect. So
Sir, would you please repeat why 360-degree rotation won't have a physical effect?
no, right now I'm not saying that it will not. 360 rotation is of course no rotation at all. So we classically expect 360 rotation not to have any physical effect. But as we see from the parameter space, a 360 rotation, that is, you're starting at 180 rotation about this axis, and then you're going all the way down to 180 rotation about the opposite axis, which is ultimately 360 rotation in this space. That can possibly have a physical effect. You can't rule it out because you can't shrink that down to. If you could shrink down a parameter space continuous to zero, then no continuous feature would actually give you a non-trivial result here, because whatever thing you can have, you can continuously shrink it down to no effect whatsoever. But you cannot do it for 360 rotations. That's the important point. 360 rotations are not conductible. 720 degrees are. What that means is it's feasible that there are situations where 720 degree rotations would really give you no effect, but 360 degree will. This is an well. Do you have such an effect in classical physics? Actually, you do. You have this very famous Feynman belt trick, right? Or this glass trick that you may have all seen, at least videos of. You can just find videos on YouTube, and you can also do it yourself. You just hold a glass in your hand and try to rotate the glass to 360 degrees. Okay, just try it, and then what will happen is that the glass may be back exactly where you were, but your arm would be twisted into a rather bad kind of full twist. Now, the point is that might seem like, okay, if you do one more 360 degree, it's going to actually twist it even more. But that's where the funny thing happens. You can show that you can, if you are doing one more 360 degree, it's possible to continuously bring your hand back so that your hand also is untwisted. Try it out. Don't try too hard, because if you do it the wrong way, you might throw a joint. But it's something you should be able to figure out yourself. If you can't figure out yourself, look up the YouTube video. There are plenty of YouTube videos, or the Feynman belt trick, or the glass twisting the glass trick. It's usually called the Feynman belt trick always, even if you're using a glass, which demonstrates that even in the classical world, 360 degree rotation is not the same as a 720 degree rotation. 720 degree rotation can always be smoothly undone. 360 degree can't always be. Okay? Yeah? Not okay. I don't expect this to be clear. You should really check out on your own. At least check out a video if you can, which you will find plenty of in YouTube. But the important thing mathematically is that SO3 is not simply connected, whereas SU2, and we are going to talk about SU2's homomorphism with SO3 in the next class, and more, but SU2 is simply connected. That's also pretty easy to figure out. We're going to do all that in the next class and talk about general Lie groups. I have to break up today because I have other things to do right now. But if there are any quick questions.
Sir, if one is not simply connected and another is simply connected, then how are they equivalent?
They're not equivalent. They're homomorphic. They're not isomorphic.
Okay.
That is, SU2 actually happens to be a double cover of SO3. That means there are two SU2 elements corresponding to every SO3 element.
Okay.
If SO3 and SU2 had been isomorphic, then of course they couldn't have had different topologies. SU2 is simply connected, and that is why SU2's representation theory is actually way simpler than SO3's. So it so happens that the complexified version of SO3 is actually way simpler than SO3 itself. Rotations are complicated objects. SU2 transformations are not. At a Lie algebra level, SU2 and SO3 coincide because of the homomorphism. We are going to explain that, and that is why when we talk of Lie algebras, we don't really distinguish between small SO3 and small SU2. They are isomorphic as Lie algebras. But the groups are different.
Okay, sir.
The homomorphism actually makes a huge, we can exploit the homomorphism to reduce a lot of information about SO3 from the simpler representation of SU2. SU2 is actually simpler than SO3, despite having more. Of course, it doesn't. It's number wise is the same. It has three parameters as SO3 has. Those three parameters are distributed, or in fact, SU2. Let me just quickly tell you this. I think all of you know this. A general SU2 element has to be of this form. I think all of you should know this, at least this is standard matrix theory. Every SU2 element has to be like this.
Yes, sir, we know.
That means described by two complex parameters alpha and beta. Two complex parameters means four real parameters, right? If alpha is x plus iy and beta is u plus iv, then this is x square. So every SU2 element is basically all four tuples x, y, u, v, which this particular condition. So what is that? SU2's group manifold is actually nothing but S3. A sphere, a three-dimensional sphere embedded in four dimensions, which is of course a much simpler, despite being in four dimensions, it's simply much simpler as a geometrical entity than this sphere, a solid ball with antipodal points identified, which SO3 has. Okay, so this is a simply connected group manifold. But SO3 is not. So we'll take a deeper look at this connection and next year. Okay. So I think I will call it a day today. Next day we are going to talk about this connection between SO3 and SO2, and that is on Thursday. And then go on to talk about Lie groups in general. Okay, bye for today.